Good evening, everyone. My name is Erik Flesch, and I'm the director of the Mining and Rollo Jameson Museums. And welcome to this fourth of 7 presentations as part of the 2023 Winter Lyceum. Today is the 12th day of March 2023, and I'm broadcasting from Platteville, Wisconsin, home of the world's largest letter M in the heart of the hilly driftless area, and a special place known as the Upper Mississippi Valley lead and zinc mining region where the Badger State was born. Founded in 1965 by the city of Platteville, the museum brings to life a rich cultural heritage rooted in local history, a tradition of science, technology, engineering, arts, and math, and a celebration of pioneering, which we recognize to be the living human spirit of ingenuity, inquiry, enterprise, and development. I invite you to stay up to date on museum programs and to support current initiatives online at www.mining.jameson.museum. This year's Winter Lyceum continues to be a truly electrifying series of 7 presentations on the theme of energy in the context of our driftless area landscape and current events. The subject of the talks has ranged from generating and storing electricity in historic mines, to solar and wind energy production, to organic farming, to creating artistic geometric abstractions from nature. It's my great pleasure to welcome you this evening to enjoy a presentation by engineer Mark Nussbaum titled Greening from the Ground Up, Integration of Ground Source Heat Pumps into Historic Buildings. Mark is going to give us a primer on geothermal energy and share some success stories of retrofitting some beautiful works of architecture with energy-efficient geothermal HVAC systems. I'd like to thank all of you who have registered to participate live today, as well as those who may be watching a recording of this event from our library of virtual programs. Welcome to current friends of the Mining and Rollo Jameson Museum's members and donors, and a big thank you to the sponsors whose financial support has made this program possible. A&W Restaurant of Platteville, Claire Bank, Edward Jones Financial Advisor Bob Hundhausen, Inspiring Community, Southwest Health, State Farm Agent Jordan Holthouse, and Tricor Insurance. And now, before we begin our program, I'd like to invite you to participate in a question and answer session and a short survey at the end of this evening's presentation. Because we're a big online group, in the interest of time, I'd like to invite you to type out your questions as they come to mind and to submit them via the Q&A function at the bottom of your screen during the talk. And at the end, the speaker will answer as many of the questions as he's able in the order in which they are received. I'm now pleased to introduce tonight's speaker. Mark E. Nussbaum, professional engineer, is the founder and principal at Architectural Consulting Engineers in Oak Park, Illinois. He's registered as a professional engineer in the states of Illinois, Indiana, Ohio, and Wisconsin. He has been in private practice since way back in 1995. The 2 principal areas in which Mark works are historic properties and the integration of energy-efficient technologies, including geothermal systems, whenever possible. Mark also uses building science principles to support his evaluation of building envelopes, which helps him to identify environmental or systemic-related issues that can impact the historic structure of a building or the collections housed within. I met Mark and his wife Deb last year when their firm served as the HVAC subcontractor under Preserve Design Studio, working on a preservation plan for the museum, and was truly impressed with the depth and breadth of Mark's knowledge. Plus, he's got a big heart and a sympathetic feeling for the mission of our museum. Before he opened his own firm, Mark served in the U.S. Navy as a nuclear-trained machinist mate, worked at the General Electric Nuclear Energy Business Office, worked for the City and County of San Francisco Bureau of Engineering, and 2 architectural and engineering firms in the St. Louis area, Booker Associates and AAIC. He attended the University of Michigan, graduated from San Jose State University with a Bachelor of Science in Mechanical Engineering with distinction. Please join me in welcoming Mark Nussbaum.
Hello, everybody. It's a pleasure to be here tonight, and I look forward to giving the presentation and then answering any questions that you may have as the presentation moves forward at the end. So I'm going to go move right into the slideshow, and I'll share my screen here and see if we can make this work. We practiced, so hopefully. Can everybody see that? Yes, okay, great. So as Erik mentioned, this the title is Greening from the Ground Up, Integration of Ground Source Heat Pumps into Historic Buildings. I've been in private practice since '94 and have pretty much been working in the geothermal field for in the Chicago area since about 2004, 2005. I've done a couple projects down in the southern part of the state as well, but I actually moved on up here to this area before those were built, so I didn't get to see them to fruition. So in the Chicago area, the technology was still coming along and increasing efficiencies, and the cost of electric was up here was a little bit higher. So the balance between electric and gas costs didn't work real well in this area unless you just really wanted geothermal. So now though we do it all over in the area because the cost balance has gotten better, and the between the energy rates and the cost of installation is more competitive with the higher efficiencies. So today we're going to review how ground source heat pump systems operate to provide highly efficient heating and cooling from any building types. And we're going to go through some case studies that help to illustrate some of the challenges of integrating modern systems into historic buildings. The system or the buildings we're going to look at today are 4 projects: Pleasant Home, the Balch Lottie House, Carroll Center, and Glessner House. And I'll go into more detail about each of those buildings as I get to each case study. So why geothermal? Why do we care? Well, it's got the highest efficiency of any system that's available for heating and cooling buildings. It has very versatile system configurations. I can really pretty much adapt this system to almost any other configuration, any other existing system we're building. I can't replace a steam system. The technology is not there to do that, but I can replace hot water systems and forced air systems. It's adaptable to new or existing buildings. There's no exterior visible components. All the exterior components are buried in the ground, so you don't see anything. You don't have to worry about acoustical noise issues or aesthetic issues with exterior components and the wear and tear on the exterior components. You can provide simultaneous temperature and relative humidity control, which is something that I'm often looking for when I'm designing a system for historic buildings in particular, where we're trying to mitigate damage caused by uncontrolled relative humidity primarily. Temperature usually is controlled with your system. Relative humidity floats around a lot. And so this system can provide simultaneous control of those, which helps control deterioration. And it can produce domestic hot water if you configure it to do that. These systems are classified as renewable energy because they garner approximately 70 to 80% of their conditioning energy from the earth. They can also be characterized as a solar energy system because about 50% of the energy that lands on the ground is absorbed by the ground, and so it acts like a solar battery, and it helps keep the ground at a fairly consistent temperature. Once you get down below maybe 10 to 15 feet, the temperature variation drops off towards pretty much a stable temperature that we're working against. Unlike air source equipment, air source heat pumps, and air conditioning systems that have to work against the air temperature, which can vary, from very cold in the wintertime to very warm in the summertime. The geosystem has to work against the earth temperature, so it really helps with the efficiencies of the system. Underground temperatures, as I said, the deeper temperatures, when these are at well depths of 30 to 60 feet, and it's consistent from that depth down. So in our region, we're somewhere between 52 to 47 degrees. About the more north you go, of course, the colder the average ground temperature is. But it works really well. And in our climate, geothermal works really well. It's a pretty balanced system. We have We have similar heating and cooling loads if the building is a well-insulated building. Sometimes older buildings, we have higher heating loads than we do cooling loads, but it works really well because we like to put in as much heat as we're taking out of the ground if possible. So we do have to put energy into the system to make it work. It's not totally free. So for every 1 unit of energy from the utility company, we get 3 to 4 units of free energy from the earth. And that's why it's considered renewable energy, because we get the majority of energy from the earth, whether we're absorbing energy from the earth or we're sending energy to the earth to be absorbed by the earth from our building. If you happen to have a solar system, solar photovoltaic system, and a geothermal system, you can actually have a 100% renewable energy system conditioning your building. That's kind of neat. The system works in the type of system I'm going to talk about today is a closed loop vertical system. There's a lot of different ways to install loops, and I'll get into that in a minute. But so basically, there's different loops in the building. You can see this little dynamic graphic here, where I'm flowing. I'm in heating mode, so I'm absorbing energy from the ground. I'm bringing that energy into it, and through the work of the refrigeration cycle that's inside the machine, I heat air that's then delivered to the house. A side benefit of that is off of the refrigeration cycle, there's a high temperature gas in there, and we're able to absorb some energy out of that, so that whenever this unit is running, we can get domestic hot water produced. The caveat to that is if it's not running, it's not producing domestic hot water. So in most geothermal heat pumps, when you specify that you want that domestic hot water feature, it is only on demand, or it's not on demand. It's only when the equipment's being used. So you usually have to have a supplemental form of water heat in addition to it, but it doesn't use it as much as it would if you didn't have the system. And so then looking at again, going back to where the energy goes, we put in $1 worth of energy to run the compressor and the circulation pumps and the fan. And then we get $4 worth of energy out of the water that's coming from the ground or to the ground, and we get $5 worth of heat pushed into the air or cooling into the air. So in the cooling mode, it does just the opposite. You know, I'm rejecting energy to the ground from the building, so I'm absorbing energy from the building and I'm moving it through a fluid in a closed loop pipe down into the ground, into the earth loop. And again, I can still get the domestic hot water. The neat thing about here is, if I'm pushing energy into the ground, so I'm taking the heat from the building and putting it into the ground. So instead of doing that, I'm taking a portion of that and I'm putting that heat into the water heater. So when it's in cooling mode, you're actually getting free domestic hot water heat, well, for the price of running this small circulating pump. It's just, so whenever this equipment's running, instead of sending that energy to the ground, I'm taking it to the domestic hot water heater, to the water heater. And so that helps me improve my overall system efficiencies and reduce your overall operating costs. And again, this diagram that shows the temperatures, or the internal diagrams of it. And you know, so these little dark lines in here are the refrigeration circuit. This reversing valve is what changes it between heating and cooling. And it just basically changes the way the refrigerant flows in the system. So it reverses the function of this air coil and this water coil. That's what happens. Changes it from heating mode to cooling mode. So over 70% of the energy consumed by a typical single family home is used to meet thermal loads. So that's, you know, 60% for heating and air conditioning and 13% for hot water for a typical home. When we put in geothermal, we get almost 50% of that energy from the ground. And so we're left with this 24% that's produced with the that we have to pay for electricity to produce. So it's you can see the dramatic change, you know, in that cost. Now we do shift fuel though. We're shifting from possibly a natural gas or propane to electric in this situation. So And it's another nice feature, but it does, you have to look at the varying costs. So geothermal stacks up really, really nicely against electric resistance heat, which you have in a lot of rural areas. It stacks up very nicely against propane, and then natural gas is a little more stable price, and it's come up. It's up in cost in the last year or so, which makes geothermal even more competitive against it. But geothermal is competitive against it even at its lower cost. So it's still a good switch but every situation should be looked at. I mean, it's not a given. I like to think that every project is unique and it deserves to be looked at individually. So looking at the different types of loop field that we can talk about, again, I'm going to focus in on vertical closed loops. There are other systems that are available, and when you get into more rural areas or areas with more land, these are often less expensive systems to install. So horizontal trench systems were kind of one of the early systems that were used in geothermal world, and they're basically trenched into horizontally in the ground. There's a variety of different installation techniques, but because of the close proximity between the pipe and the surface of the ground, you do need to put in more pipe because you get more interaction with the air. The temperatures of the ground isn't quite as stable because we're only down maybe 4 to 8 feet instead of a vertical bore, which goes very deep. You can have a horizontally directionally bored system, which if you're down below the 15 to 20 foot line, acts just like a vertical bore in the way it functions. It's got stable earth to function against, and that system is it can be very cost effective to install. I did a large school here in the Chicago area where we did a directionally bored field, and it was about, the well field was about 2/3 the price of a vertical drilled field. And then there's pond loop systems. Again, these are all closed loop systems, so there's no interaction with the water. So we're not using the water from the pond directly, but we submerge loop components into the water, into a lake or a pond, and then we use that water to interact with our system. That's again a very stable system. It's very efficient. The temperatures, you got to be careful. You got to make sure your pond is big enough. There's been situations where, since in the heating mode, you're drawing energy out of the pond. They've actually had ponds freeze over if the system, and that's freeze solid, not just over top, but freeze to be an ice cube, and then no longer works. So you got to make sure that you size the loop appropriately and make sure the pond or the body of water you're installing it in is adequately sized. But we're going to stick to vertical for the rest of the discussion, just because that's what I install mostly in the Chicago area because of the dense population, limited ground areas. The bottom line with the geosystem is you have to have a certain amount of pipe in the ground to handle the thermal load you're going to take in and out of the ground, and so a vertical bore takes up less square footage of site because I'm going deeper in the ground. So the typical system is called a U-bend system, and so it's a specially constructed pipe, and I'll show you an example of it here in a second, where it's typically factory made, and they make it as deep as to go into the hole as deep as you want. The depth of the holes that we drill are anywhere from maybe 75 feet all the way down to 500 feet. I know the slide says 650 feet. They were doing that around the Chicago area for a while, and they had some problems at that depth. And so I don't personally design any deeper than 500 feet. So what that looks like is, and here up in the upper left-hand corner is some rolls of the tubing. These are each one of these individual rolls here is for a 500-foot hole. And so there's a pipe that goes down and a pipe that comes back up out of the hole. The bottom of the hole has this really tight U-bend on it so that I can fit it into a 5 or 6 inch hole. And then usually when you're putting it in, you have to put a weight on it or drive it down with a machine, because the tubing is, even when filled with water, it's more buoyant than the water that's going to have filled the hole. And then a really important piece is here in the center on the bottom. That's what a cross section of the hole looks like when it's thermally grouted. And we use a grout for two reasons. One is because we're required to by law, because we don't want surface water interacting with the aquifers that we're almost certainly going to drill through as we drill deep into the ground. So we don't want to have contaminants, surface runoff, landscape, chemicals. We don't want any of that to get down into the aquifers. So it's a bentonite grout mixture that's got silica sand components added to it to make it more thermally conductive. And that's the second reason why we do it, is because now I've got a solid connection between the ground and my pipe with a material that will transfer the heat between the two. And so that's a critical component, and again mandated. This picture in the upper left-hand corner is once we get the holes drilled, the vertical holes drilled, we gotta connect them all. We bring them into the building. Depending on the designer and the depth that you're drilling, you'll either bring in every hole collectively. That's one method to do it, or you bring them in individually. So for each hole, there's two pipes of supply and return, or you can connect them together into a matrix where you're connecting multiple holes together, and then you bring in a bigger pipe to handle that flow. I like on the deeper holes, we're using a 1 1/4 inch pipe to go down to 500 feet. So it's a 1 1/4 inch pipe, 500 feet down and back. So that's a lot of pipe length. I like to bring those pipes, if I'm close enough to the building, I like to bring those pipes directly into my building where I can valve it off. And that way, if I've got, say 6 or 10 or 20 holes, I manifold it in my building, and then I don't have, if I ever have a problem with a hole, I can isolate one hole and not have to worry about losing my entire field. If I connect all the pipes together out in the field and I have a problem with a pipe that's leaking or a joint that's leaking, then I've got nothing. There's very little I can do to solve that problem without digging it up. We do these systems are pressure tested. They're pressure tested at the factory. They're pressure tested once they're brought to the site. They're pressure tested after they put them in the ground. They have to make these couplings here. They have to put those together with field connections. So we pressure test all of that. So we're pretty confident we're not going to have a leak, but things happen, and you have to be prepared for it. There's another type system that I've used in my designs, and there's several others that I'm not going to talk about because I haven't used them. This is called RIGAN. It's a high performance geometry exchange system, and it gets about twice the performance per hole as a conventional system, but it's significantly more expensive. All these components have a significant cost, are all highly engineered. But when you're really, really tight on a site and you have a heavy load and you're trying to get it in, this is a good alternative to the U-bend piping because I can get more capacity out of a single hole. And that's typically where we use it. Either that or when the drilling conditions are really hard and they're very challenging to drill. If we go this method, then we don't have to drill as many holes or holes as deep. So it's another heat exchanger that can be used. Basically, the water flows down the inside pipe, and then it flows out the concentric pipe around. These corrugations on the outside of that pipe cause it to churn, which we're trying to get good heat transfer again between the pipe and the ground. Here's a sample of that installed, a couple of projects. Again, the piping material in the ground is the tube. If I go back to this material, this is a fiberglass resin, I believe, or carbon fiber resin product in 20-foot sticks, and they attach that together. And then there's a stainless steel head that comes in at the top, and then the high density polyethylene pipes, which is the same material we use in the vertical U-bend piping. So moving on to case studies. And I'll talk a little bit more about system design as I'm moving through these. We're going to talk about 4 buildings today, as I mentioned. Top left here is Glessner House. It's in Chicago. It's a house museum. This is Pleasant Home in Oak Park. This is the Balch House, a Frank Lloyd Wright designed Balch House in Oak Park. And this is Carroll Center, Community Center in Oak Park. And this part of the building is new, but there's a 100-year-old original building that sits just adjacent that we also included in this project. So we'll start with Glessner House. This is an H.H. Richardson designed mansion. It was completed in 1887, shortly after he passed away. He designed this as one of his last projects that was built. It's a National Historic Landmark. It's owned and operated by the Glessner House Museum as a historic house, museum, and an event space. They do weddings in the backyard and in some certain spaces inside. So we designed this field for it was a 26-ton loop field heat exchanger size to allow for some additional areas of the building to be added. We don't have quite that much tonnage connected to it, but there's a coach house down here where they have an existing mechanical system that hasn't quite aged out yet. And then there's a second story that's not finished. And so we've got capacity in our loop field to handle those two areas when they're ready. We've got 8 self-contained heat pumps installed. We have an interior geoloop distribution piping, and new ductwork is required. There was a ducted system in this building. It was just residential style forced air furnaces and very little air conditioning. There was a couple of areas that had air conditioning, but not many. So we had a very tight courtyard to work in, and so we decided to do the Rygan system, and we did this in 2 phases. They didn't have the money to do the entire system in the first phase, so we did half the loop field. We planned for 4 Rygan holes in the original design, and we installed 2 of them, and then we installed 1 interior system. So again, this is that piping that's the outer tube. And then this is that inner tube that goes down. It's a little hard to see, but there's a corrugation on that, and it gets pushed down, and then that metal head gets put on the top. In 2021, they got a grant to install the bulk of the rest of the systems. Unfortunately, by the time we got into that, the driller who had drilled the first 2 holes was no longer in business, and he was the Rygan. He was the guy that did Rygan in our area, so we opted to change to the conventional U-bend style. So because of that, we had to add 2 more holes. So we had to go with a 6-hole hole. So remember, I said that the Rygan is about twice as good at per hole or per linear foot of hole depth. So to make up for those 2 Rygan holes, we had to have 4 same depth U-bend holes. So this yellow thing off here to the left, that's the drill rig. It's a tractor rig. It's the only rig that we could get to fit in this site. There's a gate that you have to come through. In fact, to make it through with that rig, we had to take the cast iron grid across the top that had a wooden gate with a cast iron decorative top. And that had to actually be temporarily moved for the duration of the project to creep this guy in on its tracks. This is a compressor, a large air compressor that drives this rig. So this is a diesel rig over here. It's working, but the drill power comes from this compressor. And as you can see, it's a very messy process. This rig here on the right-hand picture is it's a machine they use that forces this pipe down in the ground. As I mentioned, it's more buoyant than the water it's going down in, and so they force it down in here, and then they also send what's called a trimming pipe to the bottom with it after they've got it down there, and that's how they grout. They grout the hole from the bottom up. They push that pipe down, and they start pumping grout under high pressure. It displaces any water that's in the hole. As you can see, they're pressure testing this piping up here at the top of these pipes here. Again, they constantly doing variations on pressure testing just to make sure we don't have a bad pipe or a bad joint. In 2015, this was the inside of our dungeon-y type of basement. It was a long, skinny room. We tucked in a heat pump in this space and serviced just a portion of the building. We had a temporary, and we had planned for, they had to core the foundation wall below grade, And so we at the time in 2015, we planned, we had 4 Rygan holes we were going to use. And so they went ahead and cored the extra holes through the wall so that we were future proofed when we thought we were future proof for our when we expanded our field to 4, we wouldn't have to do that coring again. We could just connect to the pipes that were outside once we dug there. But as I mentioned, we had to change that design philosophy. Flexibility when you're designing the systems is key. So as we've done our investigative work in these old buildings, what we're trying to do is we're trying to find interstitial spaces we can route ducts and equipment, or set equipment, route ducts and piping in. So it's a constant challenge to try to find places in these buildings. And I spend a lot of time in each of these old buildings trying to identify those areas that we can route piping. So this is an eave in the 3rd floor. So below this floor is the 2nd floor ceiling. Because of the shape of the roof, I've got a little interstitial space here. And so guess what? I'm putting ductwork in there. Now this is the old ductwork that was there in this house where we're using the ductwork we can. We had to upsize some of it and increase it, but generally speaking. This is one of the abandoned water-cooled AC units that they had. They brought water in from the domestic water supply and dumped it down the drain, and it cooled this heat exchanger and that compressor. So this is like a self-contained water-cooled unit, or not self-contained, but then the compressor was hooked to a coil in the unit. So this unit actually had air conditioning at one point. It was not functioning when this project started. There was 2 of these in the house that served the primary 2nd floor areas of the house museum. This is the kind of example of the typical condition and type of equipment we had, kind of layered throughout the house. This is up in the attic, and it's in very poor condition. It's conventional gas-fired furnace. In one part of the basement, it's a slightly more recessed than the rest of the basement. Basement has very low ceilings, as it's really, but this was the school room, or where the kids of the Glessners actually went to school. And what I like about it, this metal panel, behind this metal panel is a pipe radiator, which is essentially pipes hooked up together into a serpentine fashion to reject heat. Then they're ugly. And so they had this commission, this beautiful brass and copper plate that's connected to it. It's hanging from the metal pipe radiator. And we have plans, if they get a little more money, we're going to produce some hot water and make this warm again. It won't really provide the heating, but it'll give this that sensation of what it felt like in this room. It's just one of the details in this house I really liked. So this is what the manifold looks like now. With now we have the 6 sets of pipe coming in. We ended up having to core those extra 2 or 4 holes to handle the additional 2 pipes. So this is a manifold. So we bring all those pipes together in here. And we have shutoff valves and balance valves in each of these, so that we can control how much water flow we put down each hole. We get connected to the bigger piping, and it's insulated because it does get very cold. The pipe in the wintertime can get down into the 30s, if not lower. So it will condense water. If there's humidity in the air, it'll sweat. We have an expansion tank because we're varying the temperature in this system. There's a lot of piping in the system between the holes, the piping in the holes and the piping throughout the building. So when as water heats up, it expands. And so you have to account for that with an expansion tank, which absorbs that expansion without causing the pipe to rupture. We've got a glycol fill system here, this little pink box. It's actually just pink fluid. And that's got our 25% glycol fluid mixture in it. And so we don't direct connect this to like a water supply, because what I want to know if I'm losing water. I want to know if I'm losing fluid in the system. So this is set up to have a discrete amount. If it needs to fill it, it'll fill it, and if it gets too low, it'll give an alarm, which then tells us that we have a leak that we need to attend to. And these are the 2 pumps that are flowing the water. Now, these are piped in series. They don't have a huge amount of head pressure available to them, but they're very, very efficient. You pipe 2 of them together so I can get the same flow through them, and I can double the static pressure that's available. because it takes a lot of pump energy to pump the water down that through that 1,000 feet of pipe that goes to the bottom of the hole and back. But these are variable capacity pumps, and what I'm doing is I'm controlling these based on loop temperature. I flow at a slow rate of speed when I'm within temperature range, just to kind of move energy into the field, but at the lowest possible rate. And when I get to either 80 degrees at the high end or 40 degrees at the low end, I start to ramp the speed up to increase the amount of heat transfer with the ground. This is an example of one of the new units. There's a grand stair that comes in off this building right up the front, and this closet used to have a radiator in it, an indirect radiator that was suspended. So we took that radiator out, and we were able to tuck a unit into there. And this is not inconsistent with the types of things we have to do in these houses where you're finding in these interstitial spaces. There's another unit in a closet where a unit had been housed. If you remember that old furnace that I showed originally, these are the replacement equipment there. These aren't fully installed yet, but this is installation in progress. And we broke up that area into 2 zones instead of 1 to service, so we have a little bit better zoning. Here's a couple more units in another area. Again, these are little closets in the 3rd floor. And my geopiping comes in, and then the heat pump. The compressor sits in the bottom of these units, and the fan and the coil sits up top. What's interesting, remember I said you can control relative humidity with these types of units. You have to specify that, and you can't do it with all units there, but many of the units are capable of it. And it has a separate coil here. The way the Climate Master does it is has a coil that basically recirculates. So when I'm in cooling mode, I'm rejecting heat to the ground. And if I hit my temperature set point in the room, but my relative humidity is still high, then I start to recirculate that loop water, that warm loop water, back through another coil downstream of the cooling coil. And eventually it gets up to where it's delivering neutral temperature air, so 70-degree air, say, or 70, whatever your room temperature air is. So it's no longer cooling, but it continues to cool off enough to pull the humidity out, and then it's reheated back up with loop water. So it's a very cost-effective way to get that simultaneous temperature and humidity control. Moving on to the next case study is Pleasant Home. And it's another mansion here in Oak Park. It was donated to the Park District, and they now run it as a house museum and an event center. It was designed in 1897 by George Marr. It was one of the early Prairie School designs that Frank Lloyd Wright made a little bit more famous. Also a National Historic Landmark, so owned and operated by the Park District. There's a 40-ton loop field here. And again, this one's oversized. They do a lot of big events here. This is they've got large 1st floor spaces. It's less of a house museum than it is a event space. They do classes. So we had to increase the capacity, the system components, the equipment, and the loop field to handle the larger population of people that could be in this building in severe weather. And there's a couple areas that we took out of the project. That the loop fields, we kept it full size, but they may go back in at some future point. It was going to get into some historic finishes. They didn't want to ruin with air devices. So in this case, we have 7 vertical and horizontal self-contained heat pumps. We have the interior loop piping. There was no ducted system in this building, so we had to add all new ductwork. And there's an existing gas-fired boiler and cast iron radiators, which we maintain. I like to keep them in historic buildings because it helps keep the walls warm and drive any moisture that wants to penetrate near windows. Usually the radiators are near the windows, so it drives that out and helps keep the walls warm, dry, which maintains their integrity. So totally different drilling process here. This is one of the large rigs that you might see around other drilling sites if you happen to see any drilling sites, and they pull this one circulates the we'll call it the mud laden fluid that comes out, so that they pump in order to get the material out of the ground. they drill it, they break it up with the drill bit, and then it's flowed out with a mud fluid mixture that then's pumped over here where the solids are separated, and then the clear fluid then circulated back. So this is kind of a totally different technique, but much bigger. And you can see why it worked well on this site, because we had lots of ground to work with, but other sites it's a little tight. They had to, after the well field was in, they had to, in order to get the equipment up on the 3rd floor, they used a crane lift. They opened up a window up here, and then we were able to lift it into a 3rd floor window, because we have 4 units in the attic. So we had to, and the stairs are hard and these units are heavy. So the contractor got really creative to bring them in with a crane lift. After the holes were drilled, they were in this case, I combined, I think 3 or 4 holes together into one header. So these are 2-inch headers that come in, or 2-inch circuits that come in. So I've got 1/3 of my loop field is in each of these 2 pipes. So still isolatable if I have issues, but not quite as isolatable as the other system. This is what it was like when it was starting to be piped up, copper piping. And then this is what it's like fully insulated. Again, really, really low ceilings in this project. It was amazingly low ceilings. These are the pumps being installed. In this case, I'm using 2 pumps in parallel, same type of pump or similar type of pump to the other project, but I needed more flow here than this could give me, but I could get enough head. So I had 50% flow from each pump, and they combined together to give me 100% flow. And then once they were all together, and here's an interesting thing: the contractor made a mistake and had put in too small a pipe here. And so when this was initially set up, it wasn't flowing properly. We had to have them come back and change this very small piping out on either side of this so we could get the full flow. And then this is what now it's all corrected, and it's pipe, and you can see there's my expansion tank that I have on the other system. So yeah. This is an example of we're using the system I mentioned. We can make domestic hot water. So we come off these ports. Once you specify it, it comes off these ports, and then it's piped over, and it comes into. We're using the old gas-fired water heater as a storage tank. So we're preheating. We're filling that. So we bring our cold water into this tank. We're heating it with the geo system. As the hot water demand is drawn out, it flows out of this preheat tank into this electric heating tank. If the water's at temperature, which if the system's being used a fair amount, it could very easily be, then this electric system never runs. If it's not, then if it's not at temperature, then the electric heater in here tops it off and gives it temperature. Another problem we had on this job was we didn't have any floor drains anywhere, and in order to keep the cost down, instead of trenching the floor and putting in a sanitary waste system, we have these small pumps that take the condensate off of the units when they're in cooling mode. Here's another example of an interstitial space. So I looked at the drawings and I saw what appeared to be a void. I couldn't figure out why it looked so big on the plans. So I did a little investigation. Indeed, there was this room in the 3rd floor eaves, and it's about 4-8 feet wide and deeper than that. It's up against a chimney, and it was this wall was put in because in order to have head height walls when you get out of the room, they just portion this off. And so this is what it looks like after I found it. This is what it looks like after I filled it with the equipment. Problem here is just it's going to be a challenge for maintainability. The park district signed off on this, felt like it was worth it, so we didn't have to find someplace else to put this unit, because there really wasn't a lot of choices in this location. So and they have the option of adding a door down here. This room is not on tour, so they can modify it and add a door to maintain that end of the equipment if they want. This is another closet. We actually went into it. It was a real closet, and so we again, the unit was laid in the closet. This unit services a kind of a portion of the building that's attached on the west side, and it has a lower roof. And so we had to come over here and then drop down through a truss system to get into the ceiling cavity below the roof line over there. So the guys did a really nice job with this. Again, my condensate pump here, they had to actually cut out and lower that to have it so it was below, because we didn't have a lot of room to raise this unit up. So instead of elevating the room to the unit to have the room for the condensate to flow out, they actually made a little spot. This is in a little drain pan. And these guys here, these are water sensors. There's a water sensor in here. There's a water sensor down there. So if water accumulates in the secondary drain pans that are below all the units on the upper floors, it'll shut the unit down and issue an alarm. So we don't have a potential for water to cascade down through our building. More piping or more. So this is our loop piping that's coming up. We found a wall cavity that we could sneak it up in. There was a small area down, again, an off tour space this is drywall that had been removed before, so we were able to remove it again, take out the section of drywall that had been removed, and then we were able to get our pipes in and insulated. Over here, this is up in the attic space, again, working around the structure. These guys were magicians with the sheet metal, finding room to tuck the units. Again, there's that water sensor in the pan. And then there's this unit serves one area, then there's another unit where ductwork comes in this direction and serves another area. So there's two units up in this attic space, in addition to the other two that we just looked at. Again, more, just kind of installation pictures using spaces that are available to us. The rules in an historic house, especially if you're living up to the standards of the industry, are that you have primary historically interpreted spaces, secondary spaces that are a little less important, and then tertiary spaces that you can kind of treat as utility spaces. Attic spaces are tertiary spaces, closets are tertiary spaces. And so we're working primarily in areas that we can go into that don't ruin the historic look of the building. We do interact with the building with our air devices. So in this case, we have custom air devices the pattern was picked out by the Park District. It mimics a grill pattern that's in the building or looks very similar to this. So we have the same type of grills on the floor. These are just heavier duty with a flange to take a walking weight. These are lighter duty, but they're the same basic pattern. And so, but we have to put them where we can get them. So they're again, remember that interstitial space around the perimeter of the eaves. So all these grills are working in that zone. I've got a return and a couple of supplies to serve different rooms. And then in this area, it was a stair landing, but on the other side of it, I had a utility area that I could kind of get into units. The next case study is the Balch House, and the owner was trying to make a net zero house. That was her original goal. She wanted to kind of prove that you could do it in the house if you were careful about it. Lots of windows. The plan was to insulate the roof, insulate the walls, put storm windows. The building had storm windows originally, so put storm windows back on the inside. They're inside storm windows. Use a geothermal heat pump system, and then photovoltaic on the roof, which had to be set back away from the roof edge because this is in a historic district, so they couldn't be visible from the street. Again, this building had cast iron radiators, and we wanted to reuse those, but she wanted to go net zero, so that means no gas-fired equipment. So I couldn't put a gas-fired boiler in. So we're using a high-temperature water heat pump, ground source heat pump that'll give me 160-degree water. So I could usually these systems run at 180. We're using 160. That's as good as we can get. But with a much better insulated house, that's more than enough. 120, which is the standard heat pump output temperature, that wouldn't have been enough, I don't think. We needed a little bit warmer, but so she's able to keep the style of heat she likes in the wintertime and then have a forced air system for the rest. We have ERVs for energy recovery ventilation that helps because we were tightening the envelope up so much we were worried about making sure we had enough air changes. So we use ERV to exhaust bathrooms and general exhaust, and then bring in fresh air to be distributed to the house. Again, we had to put ductwork throughout, and we used two self-contained inverter style heat pumps, which are super high efficiency, and then one split system with an air handler on the second floor. That's the loop field piping, 450 foot closed loop piping. Again, in a roll, this is that same drill rig. I work a lot with this guy. And he's drilling. This site was a little bit easier to work on. It didn't have as many obstructions, but you can see there's this concrete curb along here. We had to be careful not to chip, because that's historic right with the house. So there's still, even on these bigger sites, there still can be challenges. So this is the air handler that sits up in a closet that services the second floor, most of the second floor. This is the mechanical room, sits right below the dining room, which made me a little nervous because I was worried about equipment noise coming up through hearing equipment noise. But thankfully, you have no idea these units are running. You can barely tell they're running when you're in the room. So I've got my standard temperature heat pump, hot water heat pump. I've got my high temperature heat pump. I've got I'm sorry, this is my split unit that couples to this air handling unit. Then I've got my standard temperature heat pump and my high temperature heat pump. Because I'm producing hot water to use in the radiator system, I've got a buffer tank, which you want a little bit of volume storage so that the house could heat up in an appropriately timed fashion and use a little bit less smaller units to accomplish that. And these are the two inverter self-contained units, and they come with they don't come with, you specify them with what's called a smart water heater. So in this case, instead of only having domestic hot water available when the unit is running, these units have the ability to direct all their capacity to this tank when it calls for domestic hot water. And so I essentially have on-demand hot water. And that worked out real well for this client. Again, my little expansion tank, my loop field manifold coming in and out of the ground. I don't have any final pictures here. I got pictures that were in progress. So we had to get creative on the two end rooms on the second floor. We couldn't get there from that air handling unit that's on the second floor. This kind of delivered air to the primary rooms. We couldn't get there because of the ceiling height. The roof sits right above here. And then there's some ceiling joists here that we're notching and we're reinforcing on the bottom, just that we're suspending the plaster ceiling in the corridor. But I didn't have any place to run ductwork from above to get to here. So we had to, one of the units in the basement services the two end bedrooms. They're mirrored out in this house. So, but we came up in the back of a closet niche. This was eventually finished out with wood paneling to cover it. We said a full depth closet on one half and then a partial depth closet on the remaining half. And so then there's grills that go in there, again, custom metal grills. This is my energy recovery ventilator, one of two. I have one for the basement level that's in a crawl space in an addition that was added to the building in the 90s. And that services my first floor. And then I've got one that sits at the top of the stairs in a false ceiling that services the units on the second floor. Again, we had to get creative. The basement was filled with hot water piping to service all the radiators. And so we had to reroute a few of them up into joist space cavities in order to make room for ductwork to get across in a more efficient way. Moving on to the next one, Carroll Center. It's roughly 100 years old. We added this 2,400 square foot addition to the side of this 100-year-old building. We heavily insulated the existing building, and then we built this passive house standards. There's energy recovery ventilators for exhaust air. There's new ductwork pretty much throughout. There's 4 heat pumps, 2 that replace furnaces in this building, and then 2 new ones, one for each side of this room, because this is a dividable room inside. We have a 20-ton loop field heat exchanger, and this building we have a photovoltaic array on the roof of the flat roof of the new addition. You can't see, you can see a little sample here that they put as an awning to the windows so that they could talk about it to people. That was added, and this building is certified net zero. which means it produces more electricity on site than it uses in the year on an annualized basis. Here's my manifold that comes in to the building, all dressed up. Again, the two pumps in series. Here's the 2 units in my basement. This ceiling, because they insulated the floor in the passive house projects, you insulate the floor. I already was really low ceiling height in here, and so I'm 5'9", and I had to stoop in most most of the basement. But that just means you can get these units in to really tight spaces. If I couldn't have got them vertically, I could have gone horizontally with them. This is the unit that's one of 2 units that services the new building. It's tucked up in a ceiling of a closet. This is the piping that came underground. And one thing I didn't mention is we piped the loop, as I said, and we control the temperature. Each heat pump has a little pump on board that circulates water between there and back to the system. By doing that, I can flow the field as slow as I want to flow it. I only need to flow it as much as I need to make my temperatures work. And then the pump that's in here gives me the flow across the heat pump that I need to make it work right. And here's the slightly larger energy recovery ventilator that services the new addition. Down in the electrical room, that's something else. Oftentimes, if you're going to an all-electric building, you're adding air conditioning, you didn't have air conditioning, we have to do an increased service size. We did on this project. Of course, we put a big addition on. Again, really low ceiling heights working with. So, but we have a new electric panel. In this case, we're monitoring all the major loads. So we monitor the equipment load, the lighting load, receptacle load. This is all part of the requirements for the certification. Then my energy recovery ventilator for the existing building is tucked over here in the ceiling of the electrical room. This is the inside interior of the refinished existing building. It used to have exposed wood battens and false beams and stuff that got buried when they added the new insulation, but they were able to keep that expression on some of it to kind of keep the historic charm of the Park District building. And this is one side of the new addition. Again, the pictures aren't this movable partition wasn't installed yet, but it's a very nice area. They do it for classrooms, and it can be opened up for like a gymnasium activity. So that's the end of my case studies. I just wanted to talk real quickly about some of the things that are available. Now I'm talking ComEd here. I apologize. I wasn't thinking about the fact that you guys are in Wisconsin, but it's worth noting that a lot of utilities have rebate programs for high efficiency systems. Here in the Chicago area, the ComEd territory, they have a rebate of $1,000 a ton for residential systems up to 6 tons. There's other energy assessment program where you can get free energy audits and things like that. Again, check with your local utility to see what's available, and then I'll tell you someplace else you can check here in a second. The Clean Energy Federal Credit Union is available. It is an online credit union that makes loans available for solar and geothermal systems and green home improvements. For the solar and geothermal systems, it'll give you can essentially borrow the entire amount of the system cost, and the system is the collateral for it. It's a competitive interest rate, and they break it up into 2 parts. One is there's a tax credit that's available, so it's a short-term loan for the tax credit because you only need that until your taxes are due, and then the balance of it is can be put into like a 15, I think up to a 15-year loan. There's other incentives from states. Again, I apologize, I didn't update this slide for Wisconsin. My bad. I'll try to follow up with that and get you something. This is where I don't have it on here. I don't know why. Oh, here it is. Okay. This database of incentives. This website is where I got these other information anyway. So you can go to this website, and it's desireusa.org, and it was funded by the Department of Energy, and I think it's North Carolina, the University of North Carolina, I think, is the one that maintains it. Anyway, if you go to that link, it brings up an interactive map of the United States. You click on the state you want to look at, and then and you can filter it. It gives all the various state and federal, and sometimes utility incentives are all there, and it's updated pretty frequently. And you can go in, you can filter for the type of system. If you want to look at geothermal incentives, you can filter for that, or federal incentives or whatever. So it's a one-stop place to go find that information. And then what's really cool is the Inflation Reduction Act of 2022 that just passed last fall. The tax credits, the federal tax credits, were set to go away at the end of 2023. So this was the last year. It was only going to be good for 22% this year. In that federal legislation, they extended the credit for another 10 years. 2021 was 26%, and they jumped up for 2022 through 2032 to 30%, 26%. It starts to sunset in 2023, and then it's gone in 2035. I'm sorry, 2033. So this is a 30% tax credit now, currently, on all the geothermal components. So the ductwork, which would be the same you'd have in a traditional system, that wouldn't apply, but the loop field, the piping, the equipment, and all the labor associated with all that stuff is applicable to this tax credit. So it's a significant amount of money. It's a credit, so it comes off of your taxes. There's, to my knowledge, there's no income limit or limit on the amount that you can recover from this. There's also a federal tax credit that was used to be a little different. Now it's come into line with the residential. There's a base rate of 6%, but you can get 30% if you either meet prevailing wage and have an apprenticeship program, which is not too hard to do, or your project has a maximum net output of 1 megawatt. And that's a really big system. So most systems are going to fall, commercial systems are going to fall into this, and even and are going to be eligible for 30%. And there's a bunch of other stuff here, but it's a very similar format as the current residential system. And what's even better for me is that there's now a direct pay refundability option for state and local governments or political subdivisions thereof, Tennessee Valley Authority, Indian tribal governments, Alaska Native, and tax exempt organizations. So churches and schools and house museums and Platteville mining museums and all those types of organizations are now eligible because they were non-tax, so they couldn't get a tax credit. So now there's a direct pay option that's available that essentially gets them 30%. They have to follow the same rules as the commercial guidelines to be eligible for the 30%. But it's a great thing for the not-for-profit world and state and local governments. And I think that's it. So I'm going to go back and I'm going to leave this slide up because you give people a chance to document that. But I'm happy to entertain questions as necessary.
Awesome, Mark. Thank you so much. Great presentation. Okay, everybody, this is your chance to go ahead, and if you haven't already, start typing some questions here and using your Q&A function. Mark, first of all, these are some really great projects. Those are some prominent architects, H.H. Richardson, George Marr, Frank Lloyd Wright. These are some kind of premium projects, high profile projects in your community there. How did you get such really great projects?
I'm just lucky. It's my suave good looks, and no, I've been going after it a long time. I've been working in this area for a long time, and there just aren't a lot of engineers that do my specific little niche, which is the historic. So I've been doing historic preservation since I kind of got into this field, starting at the city and county in San Francisco. So started to build my cred that way. and I'm and the more you do, the more people, and you do a good job for people, then they come back. And so I currently work with about 8 to 10 different preservation architects around the country, mostly in the Chicago area, but with projects, ranging from the East Coast to throughout the Midwest, and nothing on the West Coast right now, but I'm got a potential project in Oregon I'm thinking, hopefully going to go out and look at this year. So yeah, it's trying to do the right thing, I guess. That's but I've been very fortunate. I recognize how fortunate I am with the projects I've gotten in the portfolio. So
that's wonderful. And it seems like each one provides some challenges. You can't help but wonder, even though these works of architecture at their time were maybe ahead of their time in some cases, sometimes the architects were thinking about creative ways to condition the home, maybe using some of the later technology of their day for heating or cooling. But you can't help but wonder if the architects can only imagine sort of the quality of the heating and cooling that you're able to retrofit their buildings with today.
yeah, it's what's really interesting is again, I think I mentioned I like to keep hot water radiant when I can, especially these old buildings. And that was the kind of the heat of the day. It was either hot water or steam. Pleasant Home, for instance, was a gravity hot water system in its original form. It didn't have a pump. It used differential temperature across the system, and it was the highest end system of its day. It was really, really quiet. There was no pump noise. It was just silent, and as good as you could get in its day. And I like to think that we're doing something similar now. They're able to use this building now in the summer like they've never been able to use it for, and that's true of a lot of the buildings. And so so we do the interventions in part for creature comfort. That's often the driving motivation. And in the historic museums, though, we also have that benefit of temperature control, because materials, as they expand and contract due to temperature and relative humidity changes, it really damages them over time and they wear out basically. And so this gives them a longer lifespan. That's the goal. Old buildings are tricky because you can't raise the humidity too high because they're not designed for high humidity levels in the wintertime. But we do what we can to safely integrate these modern systems in and improve the climate control and improve the environmental control for the collections and building itself, which is a historic artifact.
That's a great point. Even here at our museum campus, we've in recent years begun to think of the two primary museum buildings that are pictured behind me here, the 1860 Rock School and the 1905 Hanmer Robbins buildings, as part of the museum's collection, and preserving them is an important part of our long-term comprehensive plan, as well as improving the environmental conditions inside for the collections themselves. Could I please ask you, though you have spoken on this, if you don't mind just refreshing the ability of some of the geothermal systems that you discussed, their ability to help to create consistent temperature and humidity levels, and then also are the systems that these use also able to maintain sort of particulate level and filtering the quality of the air?
Sure. So specifically talking about your two buildings there, is that
Yes, please. And or if there's just general considerations for all buildings, but yeah,
sure.
I guess.
Yeah, I mean, when you're looking at adding geothermal system, or we usually start every project with what we call a feasibility study or some type of an assessment. And so if it's a building like your buildings, we did an assessment as part of a historic structures report. And so we went in and we looked at all the systems that are currently installed for the purposes of the write-up, we like to try to identify the historic systems just because it's a good narrative and it helps us understand how the building has aged and progressed over time. We document that. And then we try to come up with what interventions we would make in those existing systems that are there now to improve the climate inside the building and the creature comfort in the building. And there's lots of different ways to accomplish that. Air conditioning in these old buildings requires forced air of some type. It's blowing air across a cold coil and either ducting it, or you have localized units. And we obviously don't want to expose those. We want to hide that, if you will. We want to try to conceal the modern stuff and deliver that air in an innocuous way through either historic looking grills. Sometimes we'll decide to not interpret the grills and just put in modern grills and just say, we're delivering fresh air or cold air to your space in the summertime. That's the price of it. We have a modern grill. Because we like to stay, if there's grills in the building though from some other function, then we'll try to match those grill styles. So, but it's all about trying to find the places for the equipment, the ductwork, the piping, all those things. Your buildings are set up pretty well. You have a forced air system in both buildings, and Hamner Robbins is that's getting reworked, as I recall. The displays on the first floor. So right now there's a lot of ductwork that comes up behind the dioramas and behind the exhibits that will have to, if that floor plan changes, those could be exposed. So a different solution will have to come there. But you find the place to route the ductwork, you find the place to mount the equipment, and then you put it in. So that's always the trick. It demands a lot of time on site. Some buildings are easier than others, and then to figure out the best way to produce that heating and cooling effect. We can do it with refrigeration, self-contained units like I illustrated here, whether they're self-contained or a split system with a remote air handler and a box that's ground coupled. You can do it with, and by the way, any of these solutions work with an air source heat pump too. It's just not as efficient and it doesn't work as well throughout the year. And the geothermal will give you full capacity year round. The air source heat pumps typically won't. But so you figure out, do I want to do it with a self-contained unit or then another option is to do what's called a chill hot water system. So the box that makes hot water, it has a reversing valve in it, and it can also make chilled water, which is 42 degrees water. And then we have pipes and we circulate that through a coil and blow air across it. So that's another method of producing the cooling effect, and you can do that. Set it up for that temperature and relative humidity control with that type of box as well, with an air handler that's set up properly. And then there's a third option, which is a variable refrigerant flow system, which is you can have a water coupled system in the basement, and then they run refrigerant piping around to air handling units, and then you'll see those as mini splits around a lot. That's a real common method these days of air conditioning. Adding air conditioning to houses that's not a ducted system. It can be a ducted system, but it's often not. You'll have a little head exposed in your house. So in our situation, we would try not to have the exposed head, the terminal unit that delivers the air. You try and put that, have a small ducted unit that sits above a closet or sits in below a drop ceiling in a hallway or something like that. So there's a lot of different ways to do it. So you got to try and figure out the best, most cost-effective balance thing. And something I didn't mention, I think I alluded to it, but I didn't mention it. The other trick on historic buildings is recognizing that there's limitations to what we can achieve with the interstitial spaces and the space available to get us there. So we often have to make the decision to decide, do we want the best performance or do we want to impact the building the least? And my philosophy is I try to impact the building the least. And I try to convince the owners or the clients, the end users, that is a worthwhile exchange. That that it's, we don't want to tear the building up that we're trying to protect. And so to minimize the damage to historic materials, you'll have to maybe put a grill that's not in the exact location you would otherwise have it, to deliver air, and just rely on, but you get the best you can from that location. And when I put that proposition out to owners, I've never had an owner tell me tear the heck out of my building because I want a perfectly operating system. I want the best system you could give me in with the least damage to my building. So we strive to make that balance point, and that just takes a lot of time and effort to get there. So
that's a great point. Okay, here's a question for you. So you had mentioned different kinds of earth loops, in different parts of the glaciated Midwest where there's a lot of topsoil. Sometimes they do this trenching and make these. Is that an example of a horizontal loop where they do the trenching?
Yep.
Okay, but here we are in the driftless region where the sedimentary rock is relatively near the surface. Maybe there's only a thin veneer of wind-blown loess, available anyway for trenching. So maybe it would be more likely to do, even though we're not in an urban environment like in Chicago, but we may, because of the accessibility of the bedrock, would this area be a good place to consider these vertical style of earth loops?
Yes. Bob, the simple answer is yes. The more complicated answer is it's really dependent on the exact location. So I'm working on a project in the driftless region, not too far from you. And I didn't design it, but there is a geothermal system that's been installed. And that system was directionally bored. So the topography there, the geology there, even though it's this similar region, it's the same general region, they were able to make a directional bore system work for their site, and it was considerably cheaper. But for the next phase that they're looking at doing, I was talking with them about it, and that opportunity doesn't, they've used that area that they could, and now they're looking at vertical. So yes, I would say definitely you'd be looking at verticals there. We're also looking at verticals on another project that I'm actually working on right now, that's going in for submission for review by the organization we're working for. There'll be a vertically drilled field, so it's a really good choice for vertical. When if you're going to trench it, you got to be able to trench it. If it's bedrock that's right there, guess what? You're not going to blast it. You just have to accept that vertical is really the only option you got. So
right. Well, it's a fun exercise to say, okay, how deep does my single drill hole have to be able to do all the heat exchange in a single really deep hole? But let's face it, like drilling a deep hole is not easy, it's expensive. So, where do you find, the most optimal like drill hole depths tend to be in our neck of the woods?
I'm not sure exactly on your neck of the woods. That's something I'm exploring, because I have to have that conversation on this other project. We usually design to the depth that the local drillers drill to. So
good answer.
Yeah. So we find out what their rigs are set up for. So what we don't want to do is ask them to do something they don't normally do, because they probably won't. And then somebody that can do it has to truck in and do it remotely. So we try to find out what the local population of craftspeople skills they have, what the equipment set up. It's not skills as much as what their equipment is and rigs are set up to drill. 150 is a real common depth, and it nominally works out to be about 1 ton of air conditioning in a residential application, 150 foot of depth, hole depth. And that's very, that's a big rule of thumb that it's definitely not the case in all situations. So it always has to be studied a little deeper, but it is something that's in consideration. And so when we, so that usually that depth is a lot of, you get in the outlying areas, that's it, because the water well guys that's the type of, and the same guys that drill water wells will often drill geo systems. So the depths that they drill for water wells is often the depth we work with for local drillers. As I mentioned, it's a certain amount of pipe I need in the ground. So if I have, if 150 foot is what people like to drill, and I need 450, I can do it with one 450, or I can do it with three 150s. I don't care. The only comment I would have is that in our area we have bedrock that sits about anywhere from 75 to 125 feet deep, and the unconsolidated soil that sits on top, it does not transfer energy as well as the bedrock does typically. And so we drill down to the bedrock and then we keep going, and then it makes our overall hole depth work better than it would if I was just in the shallow unconsolidated soil. So I might need more pipe in the ground if I'm drilling shallow than I do if I'm drilling deep, because I get a little better performance on those deep holes.
Got it. How it seems like you know a lot about drilling. Do you have like any kind of sympathies for drilling and drillers? Do I remember you're saying something about having some ancestors in that field?
Yeah, I might have had. I mentioned I lived in northern Michigan. Well, maybe I didn't. I lived in northern Michigan for 10 years. I moved there when I was 8. I grew up in Gaylord, which is a little town 55 miles south of the bridge, and we moved there from Wyoming. And my father was a doodlebugger, and that's the term that was used for these guys that were seismic. What's the word I'm looking for? Anyway, they were the exploration division of the Shell Oil Company. Okay. And so when they were thinking that they wanted to drill, they might want to look for oil, they would come in with this crew and they would drill 2 holes separated a certain distance apart, and they put sounding or instruments down, data loggers down the one hole, 10-foot increments down the depth of the hole, and then they put explosives down the other hole in 10-foot increments, and then they'd set them off, and they'd document that, and they'd send it to Houston, and Houston come back and say, okay, drill a 1,500-foot hole right there, and you got a 75% chance of hitting oil. So that was kind of and so that the nature of that crew, I've lived 30 places, and I've lived in my current house almost 30 years. And so I have a lot of 1 year and less stays growing up. And so I lived 8 places by the time I was 8 when we moved to Michigan. And that was, I was born in North Dakota. I lived in Wyoming and Oklahoma and Arkansas and all that. And we were just moving around. We were like a gypsy troop that moved around. And my father started out as a drilling helper, and then he became a driller, and eventually became a drilling supervisor, and then the explosive guy that ran all of that. And he did that his entire career, 40 years of Shell Oil Company. And so he would take us out, we get a day off from school, and he would take me and my brother out in his truck to the well field. And so we get to hang out with these drillers and the drill rigs and stuff. So yeah, I kind of grew up around this stuff, and it's just kind of ironic that I circled back around, and now I'm working with the rigs again. I don't work on them. I didn't work on them then. I don't work on them now, but I'm around them, and it's really kind of neat. And the drillers are a unique breed of people, and I find I resonate really well with them. So it's fun.
Oh, that's wonderful. They are a unique breed, and they're fun and smart. It's amazing how much goes into drilling a hole, and you get so much information out of a drill hole, and the fact that we're able to use that hole as a channel way for exchanging heat with the ground, I guess mining heat from the earth, if you will. It's just kind of an interesting idea. And now you figured out how to put that interest, together with architecture and history. It's really kind of fascinating to think about it.
It was really funny. It was what drove me back into working with geothermal was Unity Temple in Oak Park, and I didn't highlight it. So we did a $25 million restoration in Unity Temple 5 or 6 years ago. But in 2004, almost 20 years ago, they hired me to do a feasibility study to see if geothermal was possible. And so and we did a whole big study and report and found out, yeah, we can do it. It's going to be hard because Unity Temple is a Frank Lloyd designed Unitarian church here in Oak Park, and it's a national landmark, of course, but now it's a World Heritage Site as part of a collection of many of his buildings have been collected into a World Heritage Site. And it's a concrete building with almost no interstitial spaces, and so we had to find what interstitial spaces were there and figure out how to effectively put the equipment where we needed it. And it's the mechanical room in that building I affectionately call the USS Unity Temple, because it's like a machine room on a ship. It's very tight quarters and but we got it all in and it's working great. And that's a system that uses a geothermal created chill and hot water. So we circulate chill and hot water through closed piping systems to air handlers that are distributed around the building. So yeah, it's definitely a challenging project, and but one of the most fulfilling projects I've ever worked on, because when it's hard to do and you accomplish it at the end of the day and everybody's happy, there's just almost no better feeling than that. And I appreciate the opportunities that I've had to work on buildings like that.
That is truly, yeah, a major accomplishment. What an amazing building, and what an achievement that you were able to make geothermal work there. Sarah's got a question for you, but maybe kind of relates to your Unity Temple project. What other projects do you have in the driftless area? And is there a dream project you have yet to have a chance to work on?
In the dream, well, I'm currently working at Taliesin, which is Frank Lloyd Wright's school there in Spring Green, and I'm doing studies, so I'm doing that first step, right, the assessment of everything that's there and all that. And they do have a geothermal system currently, and I'm hoping, but the architect, one of the architects that works on the projects there is an architect I work with a lot. So I'm hopeful that we'll be brought in for future projects. So that's a dream project. I mean, I'm enjoying my time there already because I get to come up and spend time there at the campus, stay at the campus and work. So it's a beautiful area. I'm also working up in Circus World in Baraboo, which on a couple of historic buildings, one of which is we're proposing geothermal for. Not sure what the other one will or not. I haven't really started that one yet. I've got a project in Whitwin, which is near Sauk City. It's a little historic camp used for a variety of things, including revivals and things like that. Those buildings are not even heated, so we're not looking at geothermal for them, but we are looking at doing a visitor center, if you will. And if we do the visitor center, geo will at least be on the list for consideration. I don't know, we're in a floodplain there, and you're not allowed to drill geo in a floodplain, and that's that whole concern over surface contaminants getting down to the aquifer. So right. They typically don't like you to be, and we can't disturb you. There's limited things you can do there. You can't add any soil. You can't change the topography of the wetland. So that's a consideration. But there is a small portion of the site that's not included there. And I think geo and probably solar PV will both be on the table there when we get to that spot. I'm always open to more projects. So if anybody knows of any really cool projects up in the Driftless region, I love the area. I've spent a lot of time up there in the last couple of years, and I thoroughly enjoy it whenever I'm up that way. So
that's great. I seem to remember we were talking about Cornish pasties. Is that because you lived up in the UP, or do you have Cornish ancestry?
I don't have. I probably do have some Cornish ancestry, but Gaylord's not actually in the UP. It's 55 miles south.
Okay.
but it's close enough that the pasties are a huge draw. And my parents, we attended the Methodist Church, and they had an annual fundraiser where they made thousands of pasties every year. The congregants did, and sold them, and it's delicious. And I have my stock. I made for myself I made myself a bunch of them that are on the freezer downstairs. And
Oh,
yeah, and this year I tried to hand it meat grinding. I got a meat grinder, and I ground my own meat. So
fun.
and of course you got to use rutabaga. I'm a
Okay,
believer there that's an essential piece of it. But
sure. Sure. When you read the ingredients according to the Cornish, there should be a little bit of rutabaga. I know in southwestern Wisconsin, it's common to leave it out, but that's interesting you bring that up. Dina's got a quick question for you. She asks if you have a mentor program, or are there other formal educational programs emphasizing your approach and applying your engineering vision?
wow, I wish. I've struggled to find anybody that wants to do what I do. It's been a real challenge. I've been looking for years, and it's just not it's hard to say it bluntly. It's hard, and you have to have a certain amount of experience to do it. I mean, especially old buildings. I mean, I think geothermal, that's going to grow, and there's plenty of people that are out there to design geothermal systems. It's the historic side of it that I've been challenged to find somebody, and I would love to have a mentorship. If I could find people that I could be a mentor for, that would be great. And I've offered that up to a couple of young architects that took a particular interest in it, some historic preservation folks, and we're kind of in the talking phase of trying to do something, but it's been a real challenge, and because it's bigger firms, and it's my firm is myself and my wife, so we get to pick and choose every project we take and how much, and we work not exclusively with not-for-profits, but 75-80% of our projects are with not-for-profits, and usually people doing really cool and great things. Either they're promoting history, or they're doing good for the community. So that's a real mission for us, and so we can decide how much money we're going to make today. On a project, we'll often try to have a little bit of a sliding scale for places that don't have a lot of money, that want to put their money towards their offerings, not towards the design of those offerings. So we try to be as competitive as we can in those situations. And I've had many of my peers, there are architects that I work with, and said, you got to find somebody, because you're going to retire at some point, and there's not going to be anybody doing this. So I've had a couple firms that I've been bringing on as collaborators, if you will, that I stay on as the historic preservation mechanical consultant. I let them take the lead. I kind of set the tone and tenor of how we're going to go about it, and then let them do the fine details. And we're trying that on to see if that'll work. That allows me to continue doing this, maybe do more of it if I've got people who can do the production drawings. That's a time-consuming part, and use my expertise at the front end, and then and also monitoring it when it's being built to make sure they're following along the guidelines that we've established. But if anybody's knows of somebody that's because the trick is, I'm a licensed engineer, which means I can design, sign, and seal drawings, which is required in the states I work in, and you have so you have to find an engineer. You got to find an engineer that has enough experience in all the right areas, or can be taught, and I think it's all teachable. I mean, in fact, at one point I'd given up on finding an engineer, and I was focusing on finding a historic preservation person, because I thought it'd be easier to teach a mechanically inclined HP professional the details. They couldn't sign and seal drawings, but they could understand the process. I thought it'd be easier to teach them the mechanical stuff than to teach a mechanical guy who doesn't care about history to learn to love history. So so I'm trying it a bunch of different ways. I'm just not haven't find the right piece yet, but I'm always looking. So if anybody's got any thoughts or suggestions, I'm happy to have conversations. So
Wow. Okay. Interesting. Dina was liking your answer there. She asked if maybe you should consider declaring yourself an international heritage artisan resource. Maybe this would help to generate some interest or reach outside the U.S.
wow.
Also, it was inquiring about if you've been able to develop collaborations with the engineering program at the UW-Platteville.
I've spoken with the professor there who came and his students had done some work, a report for your buildings, and I had a really nice conversation with him, and he did seem very interested. And so I have his name, and I haven't set anything up yet, but certainly something that we could consider.
Yeah.
I do guest lecture at the School of the Art Institute Historic Pres program.
Okay.
Usually annually, I teach one or two courses there for a couple of the professors. But again, those aren't the technically inclined. They're typically people who are historic pres folks, and not, just trying to give them, an introductory into the types of systems they're likely to see in old buildings, and what do you do with them, So, yeah, no, it's collaboration with others. It's right now it's a time thing. I'm a little bit. We've had. With the pandemic, it's odd. We've been busier the last 3 years than we've been in 28 years. So it's been kind of a wild ride the last 2 or 3 years. I've tried to keep up with it all, because there's just, again, since it's just the two of us, there's a limited amount of time I have for doing things. But
right,
it's I'm always open to it, and I'm actively trying to pull back a little bit on certain things that I do, so I make more room, create more time to do the things I really like, which is the historic pres and the sustainable stuff. So.
Makes sense. Well, I think I'll ask one final question here, if I may, and that is based on what you've seen of our museum. Do you think that the Mining and Rollo Jameson Museum would be a good candidate for a geothermal system as we look to a new HVAC system in the future?
Yes, I think it would be a simple answer. They, care being taken that you have a very good idea where your mine shafts are. Of course, because we want to stay wide clear of those. Yeah, you have enough property there to make it to set the loops in the ground vertically. I think it'd be a vertical arrangement. And the systems are all systems that could be replaced with geothermal. So, and the cost would be, the cost comes in a lot of different ways. Geothermal loop field is using the biggest single expense in a geothermal system. And then the interior systems, which are made up of the equipment component, the piping that connects you to the geothermal loop, and then the ductwork systems. In your case, the ductwork systems are largely there, so that's one big piece of the puzzle that you wouldn't have to replace. So that's always a cost saver. I mean, for example, that the Pleasant Home project and the Glessner House project I spoke about in case studies. Glessner didn't have any, or Glessner had ductwork. Pleasant Home didn't have any ductwork. Pleasant Home cost twice as much for about roughly the same size building, the same number of units. So it was maybe not quite twice, maybe 2/3. But that, when you have existing systems in place that you can then adapt, that's, if you're creative with it and you don't just throw away good stuff that can be reused. I mean, I'm working on a synagogue right now that was designed with an underfloor air supply plenum system. So little mushroom caps that sit under the seats and blow air out. And it was a heating ventilating system only. It didn't have air conditioning. And they have a donor that wants to install geothermal. And so they're donating the money for the geothermal system. And so we it's very elaborate, and there's ductwork to go from this plenum up to the balcony where there's more underfloor plenum system and stuff like that. And we have these beautiful walls that are being restored right now. And one of the early things we had to decide was, do we need to tear the walls up to replace the ducts that go up and serve that upper level, and the pipes that go up to serve the upper level? And we were able to find different routes for the piping that we could work with, so we don't need to tear the wall up to get the pipes replaced. And the ducts they were heating only, so they were insulated, but they were insulated on the outside with horsehair fire blankets, which was common 100 years ago. And and so what we decided to do is we're using a product called AeroSeal. It's a method that they can go in and they can, because the ducts, they'll leak air, if they're not sealed, and there's no way to seal them in situ inside the wall. So we have to seal them up from inside with this product that will pump in there, and it'll seal up all the holes. And then we have then I have to worry about condensation. Since I'm not insulated, I have to worry about condensation on the ducts. And so, and another concern I have, I'm supplying cold air to people's feet, so I don't want to be too cold. So we're gonna take the air down. Remember that dehumidification control, that simultaneous control thing? We're gonna pull the humidity out, pull it down, and then we'll reheat the temperature up, not quite to room temperature, just to 65 maybe instead of 55. And so it'll come out warmer, so it won't, I'll be above the dew point, so I won't get any condensation on the duct. So we're managing to introduce this system and reusing the components in the walls so we don't have to tear out, and then connecting it all to the new system. So that's, again, trying to reuse the stuff that's there, make it worthwhile, make it so it functions and doesn't cause us problems. Those are always the keys. Sometimes trying to use old stuff is cause this problem, but so long answer, sorry about that.
No, this is all very fascinating. It seemed like you'd be a great person to sit around with a beverage sometime and talk for hours. So I thank you so much for sharing some of your time and your expertise with us today, Mark. Thank you so much. And Mark, when you were at Taliesin, by any chance, did you ever have a chance to meet Gary Zimmer, the farmer there? He's the organic farmer who's been there for several years now.
I have not.
Well, actually, Gary Zimmer, will be our speaker next week.
Oh,
so
wonderful.
I invite you and everyone who's tuning in with us this evening to join us same time next Sunday, 5 p.m., March 19th, for Winter Lyceum 5 of 7, when biological farmer Gary Zimmer presents Energy and Biological Farming, how farmers can reduce energy use and build soil carbon by farming differently. So thank you so much, Mark, and to all of you for participating in this program of the Mining and Rollo Jameson Museums. And good night.
Hey, everybody.